at cubics and transformations, I'm really just looking at a review of grade 11 material in the context of a new kind of function, a cubic function. So let's see what we have in store. So we've got here f of x equal to x cubed. So I just want to know, what does the graph look like? And yeah, in grade 11, you may not have looked at this. You looked at quadratics, square roots, absolute values, sine and cosine, exponentials, but this might be a new one. So just to get ourselves used to this one, let's just make a table of values and just see what that table of values gives us. So let's try to do this neater. So we'll just do x and y. We'll just do -2, -1, 0, 1, and 2. And then just, well, if you're using a table of values to make a graph, just plug in your numbers. So -2 cubed is just going to be -8. So because we're cubing it, the negative sign stays, because a negative to an odd exponent stays negative. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. So there we have 5 points. So let's graph those 5 points. And then we can see exactly what this graph looks like. Okay. So we've got curve going up, and then flattening and going up again. And we're going to actually see this kind of shape where it flattens. It's not like it's flat, but it approaches that origin, not as steep as the rest of the graph. And yeah, we're going to see that actually throughout this unit in different contexts. But this is just a plain, regular cubic function. Okay, and so now we want to do some transformations to it. That was a big component of the grade 11 functions course, was transformations. So let's see, what can you do with a cubic function with transformations? So what we can see here is we have a -2 inside and a +1 outside that cube. So what we need to remember for transformations is, if you're inside the function, that's a horizontal transformation. In this case, we're subtracting. And remember, with horizontal transformations, usually it's like the opposite. So -2 is going to be a shift 2 to the right. And then for those transformations outside the function, so the transformations that occur after you cube, are not part of the cube, then that's going to be a vertical transformation. So that's going to be shift 1 upwards. Okay, and then just take that same graph from up above, and you could apply that here. So what I'll do here is I'll just go through the mapping notation. It's the way that I like to do transformations, and it just says, how does a generic point xy on the original graph transform? And well, we just said it shifts 2 to the right, so we can add 2 to the x value, and it shifts 1 upwards, so we can add 1 to the y value. And so there we have it. If we have a point, we know exactly where it's going to go. And so you can take those 5 points we had in the table of values, -2, -8, -1, -1, all 5 of those points, just copy them from up above, and you will have your new graph. So what we'll see is, if we transform them this way, we will get 0, 9, -1 plus 2 is 1, 0 there. And just repeat that for all these points. All I'm doing is adding 2 to the x and 1 to the y. So you will have 4, 9 as your last point. And so if you graph that out, that will look something like... I should be careful. I should be very careful with the -8. Messed up the very first one. The -8 plus 1 is -7, not 9. I missed the negative sign there. So then we will have 0, -7, 1, 0, 2, 1, 3, 2, and then 4, 9. And so it'll be the same kind of shape, but now we've just shifted that origin over up and to the right. So there we go. And lastly, we have this one where we have a -1/2 in front of the x cubed. And so let's identify the transformation. So let's take a look at the negative. So a negative is a reflection. We just need to be careful, is it over the x or the y-axis? Since it's outside of the cube, it's not like inside brackets, that means it's going to be a vertical change. And to change vertically, you're, let's say, going from up here to down there. Well, what are you flipping over? You're flipping over the x-axis. So we're going to say a reflection over the x-axis. And then the 1/2, well, the 1/2 is just going to be a vertical stretch by a factor of 1/2. And there we have it. So we could just do the exact same thing. I'm not going to go through this one fully. I'll let you go through it yourself. But you just find that general mapping notation. So some point on that original cubic graph would go to, well, what horizontal changes do we have? We don't actually have any horizontal changes. It's all vertical. So we're flipping over, that's the negative, and we have a factor of 1/2 stretching, so negative 1/2 y, and that's it. So I'll do one example here. So if you were to have the point -2, -8, like we had before, well, that would then become -2. 1/2 of 8 is 4, and the negative applied to a negative makes it positive, so -2, 4. And then you could do that with the rest. So that's a look at just getting ourselves to think about mapping notation transformations. So let's just do a big summary of mapping notation. So you could have shifts, which are basically addition or subtraction. So you could have something like, well, what we had up above, x plus 2 cubed minus 3, something along those lines. Is a little different numbers, but essentially it's translations or shifts. I usually like to use shifts because it's a shorter word, but translations is the more mathy word. So yeah, you have translations horizontally, which is the d value. So I'll just write that in to the side there. And vertically, which is the c value. Yeah. So we have that. The next thing is we have stretches. We could have either vertical or horizontal stretches. So in this case, let's say we have a function sine of 2x. So the 2, the thing that's going to stretch this function, that is inside of the sine. So inside means it's going to be a horizontal stretch. And what we need to be careful of with our horizontal stretches is that it's stretching basically by the opposite of the number that you see. So you see the 2x, the 2 there, it's going to be stretched by a factor of 1 over that. Or in general, 1 over k. So just be careful of that with horizontal stretches. You might also see the word compression. I don't really like to use the word compression. You don't have to worry about thinking between stretches, compression. Just always use a stretch. Because the factor, that number, the 1/2, that's telling you exactly what's happening to your points or your graph as a whole. Okay, and then if you have the number in front, let's say it was, I don't know, g of x equal to 3 cos x. The 3 is outside of the cosine. It's a vertical change, so it's a vertical stretch. And for vertical, it's going to be by the amount, the actual number. So nothing like the horizontal one where you have to flip it. You just keep that number. So the a value, we sometimes call it. All right. And we can combine all those different stretches and translations. Actually, we should go back. We should add one more thing. You could also have a reflection in both cases. So let's just add that on. So you could have a reflection if it's horizontal. So if it's inside, if you had a negative sign inside, reflection over the y-axis. if negative. And let's do the same thing over here. Reflection over the x-axis. Again, over the x-axis would mean a vertical change, just like it's a vertical stretch, if negative. Okay, so yeah, don't forget about reflections as well. But yeah, so reflections, stretches, and translations, they can all be combined in a single function. So you could have something like g of x is equal to 3, we'll do a square root this time, times 2x minus 4 plus 5. That has addition, subtraction, both inside and outside the square root, multiplication, the 3 and the 2, both inside and outside the square root, and all of that would perform different sorts of transformations. And that means we can also combine all those things to create kind of a mega mapping notation, just combining all those things. So you have your vertical changes on the outside and the horizontal changes on the inside. So I always like to keep that in mind. So horizontal is inside your function, vertical is outside, whatever the function is. So in general, the horizontal ones, they kind of do the opposite. So it's 1 over kx plus d, but just keep in mind the d value has the sign flipped when it's actually in the equation. And then for the vertical changes, you have the a in front. That's your stretch vertically or your reflection vertically, plus your c value. And that'd be kind of the general mapping notation. Looks kind of odd and kind of big, maybe intimidating when it's just like generic letters, but let's go through an example eventually with some actual numbers. You can do all of this with a table too. Sometimes that's a little easier to organize, where in the table you can just have your original points, whatever they are, x and y, and then you can just map to a new table of values and then just create your new table of values by just stating the exact same thing. So the x is just going to be 1 over kx plus d, and the y is just going to be a times y plus c. So if you want to organize it in that way, that's a good way of doing it as well. Yeah, so you can do it that way, or the way that I did the original cubic question, where I just went point to point using that mapping notation. Okay, so let's do an actual example with the full mapping notation and seeing where a point goes to. So we have this function g of x that's essentially transforming the original function absolute value of x. So what we want to do is we want to figure out what is happening transformation-wise. So you don't have to write it down. You can just kind of look at it kind of piece by piece. So I'm going to go through the horizontal transformation. So inside the absolute value. So inside the absolute value, we have the plus 4. That means to shift left to the 4, which is going to be minus 4. So be careful about those horizontal ones. The vertical ones, you have the negative 3 in front. That's the reflection as well as the vertical stretch. And the minus 2 at the end, which is the shift down by 2. And those vertical ones, you can keep those same numbers exactly the same. So negative 3y minus 2. And so there we have the mapping notation. So that tells us some point xy gets transformed and goes to there. That's where it maps to. So now we can see, well, what happens to the point negative 2, 2? So negative 2, 2, well, it's just going to go to, and just plug it in, negative 2 minus 4, negative 3 times 2 minus 2, and we will see that that is just negative 6, and we have negative 6 minus 2 is a negative 8. And that is the new point. So that's how we can make use of mapping notation. Hopefully this is familiar and just a reminder for you of what you would have gone through previously. But it may have been a while. Okay, so we're not going to do this. It's a video. So you'll just have to go through this. But the key thing is when you are drawing graphs is you need to identify the parent function and you need some starting points. that's the key thing, because when you go through and apply that mapping notation, like we just did in this little mini example, you need a point to actually map. If you don't have a point to map, well, you can't do much. So you need to be familiar with those starting functions. And then when you have the transformations, you can write out the transformations in terms of the mapping notation. So that's just this step where I have the x minus 4, negative 3 minus 2. That's turning the transformations into basically math, into algebra. And then just map your points and graph those new points. So let's go through a single example here. So we have negative 1/2 x plus 2 cubed plus 1. So what I'm going to do is I'm just going to start with, I'm going to do this one with tables of values. So we're going to x, y here. And it's a cubic, so that's what we're doing. We're identifying what's the function. So the original function is just a cubic, y equals x cubed. And then we can write down some points from that. So I'll do the same 5 points we started with in that very first example. And then plug in the y value. So negative 8, negative 1, 0, 1, 8. And then we will map that to, and this is where we have to just determine what are the transformations. So we can start with the x's, so we can start inside the function. So we have the 1/2, which is multiplying, so that's your your horizontal stretch. But it gets flipped, so it's going to be 2x. And then you have the plus 2. But remember, that gets flipped as well, so it becomes minus 2. So 2x plus 2, 2x minus 2. You're shifting 2 to the left and stretching horizontally by a factor of 2. And then let's look outside. You have the minus sign as well as the plus 1. So you're reflecting, so negative y, and then you're shifting up 1, so plus 1. And so now just apply that to those 5 points. So 2 times negative 2 is negative 4, minus 2 is negative 6. I'm just going to go down each column. You could go across, do a point one by one. Doesn't really matter. So negative 2 minus 2 is negative 4. 0 minus 2 is negative 2. 2 minus 2 is 0. You'll see it's just a nice pattern here we have. And 4 minus 2 is 2. And then negative y plus 1. So just take negative of the original number and then add 1 to it. So 8 plus 1 is 9. 1 plus 1 is 2. 0 plus 1 is 1. Negative 1 plus 1 is 0, and negative 8 plus 1 is a negative 7. We've got 5 points. Plug them or place them onto your graph and see what we get. So we can't fit negative 6, 9. That's fine. We'll do negative 4, 2 as our first point then. Negative 2, 1, 0, 0, and 2, negative 7. So really the graph would have actually come from up above there. This is kind of the flattening area, but it's stretched out horizontally, and then it goes down like that. And there we have it. That is our graph. Now let's go down to this one. X cubed minus 5x squared plus 2x plus 8. So you might be able to identify this. Okay, it's cubic, but we have these extra things. We have the x squared part of the x. And what's really tricky about this graph is if you want to graph it like we did the previous one, you'd want to identify the transformations. But we actually can't identify the transformations when it's like this because we don't have it in terms of the 1 part cubed plus or minus something else. So it's not like, let's say something like x whatever cubed plus or minus, I don't know, a number there. That's what the form of the other one was, and that's what allowed us to easily identify transformations. And what actually ends up happening is it's actually impossible to get that function that we have here into that form. And you can't use transformations to graph it. it ends up looking something like, I don't know exactly, but it has a wiggle like that, which, I mean, if you just use transformations, if you just try to stretch or compress that original graph of x cubed and shift it, you wouldn't be able to get kind of that wiggling occurring. So that's what we're going to be looking at in this unit. And then the next one is, how do we graph these kinds of functions? How can we do that? And so we're going to see that. We're going to look at the characteristics of not just these cubic ones, but of higher degree functions as well. And we'll be able to determine how to graph them without just using mapping notation from grade 11.